So hold on. Let me know. What do you got?
All right.
What do you? So what you have to compare it to something, right?
Compare it to.
What are you going to compare it to?
I'm going to compare it to 1 over 3 to the n.
1 over 3 to the n. And why are you going to compare it to 1 over 3 to the n? What can you tell me about 1 over 3 to the n? The summation.
It is known. It is greater than 1 over 3 to the n plus 1.
1 over 3 to the n plus 1. Why? Wait. Why? That's true. But why do you need that?
Because.
Oh, I'm sorry. You're relating it. But what can you tell me before relating it to 1 over 3 to the n plus 1? What can you tell me about the summation of 1 over 3 to the n?
It's
the series 1 over 3 to the n. Why are you using that one? It diverges. Why do you know it diverges?
Because I went through the whole limit process. It's nice and easy.
Can someone tell me why it diverges? Does it diverge or converge? Doesn't it converge? Yeah.
If it diverges, you're useless. Yeah. Bigger, you're smarter, or something.
So look, you're absolutely right. That summation right there, each individual element is going to be bigger or less than it. This thing is going to be bigger than this summation, right? Or is it less than? Which one is it?
It's bigger than the summation of 1 over 3 and plus 1.
Yeah, 1 over 3 to the n plus 1, because these are smaller, right?
Yeah.
So look, if you have a ceiling, the only thing really useful that you need is you better hope that this not diverge. You hope it converges, right? You want to be, if it's below, you want it to be below something that converges. You want it to be below something that converges. So how do you know that 1 over 3 to the n converges? Can anybody? Geometric series. The r value is what? 1 over 3. And what's the a value? What's the first one? 1 over 3. So if you want the sum of this thing, can you actually find the sum?
Yes.
Yeah, what is it? 1/3 over what? 1/3 over 1 minus 1/3. So it's going to be 1/3 times 3 over 2, right? Because you get 2/3, it flips over when you're dividing. It cancels. So how do you know it can? Well, you actually found the sum. You actually found it. So yes, it converges because you found the actual sum. So you know that it is less than something that converges. So therefore, it converges. It down to what you really want to look at, and you're only really concerned about what happens as this gets off to the crazy land, off to the races, right? So when you're looking at this thing, you can kind of let's logic it out in your head a little bit. If you logic it out in your head a little bit, what's the only term in there that's really going to impact anything?
N to the third.
The square root of n to the third. Like these things right here. I mean, this is just the hand waving logic kind of it. This is along for the ride. For the ride. So is this, right? The only thing that's really going to matter here is the square root of n to the third. So how do you, what would you have to, does this allow you to write?
Right.
Now it becomes n over the cube root of this right here minus 4 over this, right? All over. And what happens inside here? It becomes this. N cubed over n cubed plus n squared over n cubed plus 8 over n cubed. Is everybody with me so far?
Yeah.
Now, why is this nice? What simplifies?
N cubed.
Yeah, what's n? Oh, yeah, the top becomes 1 over the square root of n, I think, minus 4 over square root of n cubed. Did I do that right? I think so. I think that's right. Right? Am I okay with that? Thank you. So this becomes the square root of what? 1 plus 1 over n plus 8 over this. And you're doing the limit as n goes to what?
Infinity.
Infinity. What does this go to? What does that individual one go to? 1 over the square root of n as n goes to infinity. 0. What does this go to? 0. Right? What does this go to? 0. What does that go to? So what does this end up going to, this limit? What n behavior does this go to? 0 over. What's still left in the denominator? The square root of 1, which is?
1.
So we just showed using algebra and limits that this converges to 0. Each individual L series, absolutely. In this case, the p, what's the p-value here? 1/2, which is less than 1. So therefore, what happens? It diverges, yes. So what we did up here, this is absolutely correct. This just shows that the sequence goes to 0, but it diverges. Nice. Okay. Okay, you factor it, and then you take the LCD, and then magically you have this thing that you can compare it to. You have to think about what you know already. And in this case, yes, it's the harmonic that you compare it to. Is it blindingly obvious? No. Does this work Is this pretty clear when I write it down? Sure. Just because it's easy to understand does not mean it's easy to find. Some of those beautiful math problems, math solutions, 6, 7 lines, and they're amazing. They're amazing proofs. Like, that makes so much sense. It's so powerful. It works all the time. Like, remember that proof for infinite number of primes? You can remember that, right? If you have them all, you multiply them together, add one, you've made a new one, right? So therefore, you can always make another if you have a finite number. Things like that, what they don't tell you, people spend years looking for beautiful things like that. The guy who proved Fermat's last theorem, Andrew Wiles, you've heard of this guy? Fermat's last theorem, a to the n plus b to the n equals c to the n. Integer values must be greater than 2. There are no solutions. People look for years. I mean, hundreds of years. Yeah, in the mid-90s, you know how long it took them to find? It was like 7 years of continuous work. 7 years. So, just because it's easy to understand does not mean. First of all, this is kind of cool. Convergence of absolute value implies convergence. So if the summation, if the series of the absolute value of an converges, then so does summation an. Why is that really cool? Well, do you really like having to deal with oscillating functions? No. Be honest. You don't really want to have to deal with do. So what can you do to make life easier? Take the absolute value. Because when you take the absolute value of this, for example, that looks all nasty, right? Man, it's got a -1. It's changing its sign. If you do instead n equals 1 to infinity of the absolute value of this right here, what does this become? It's the summation again, right? But what does it become on the what happens?
It basically is 1.
This one right here does. Because this theorem tells us if the absolute value of a series converges, if the sum of the absolute value of each element converges, then you know that the original one converges. So because this converges, because it's the absolute value of this, you know that this converges as well. It's kind of nice. It makes the math a little bit easier. We like making math easier. We're nodding. It allows you to attack. It allows you to attack this right here. Is this a p-series? No. Is it a geometric series? No. It's not. There's no constant ratio. I mean, it's implied that the next term is 1/4 factorial, 1/5 factorial. So in this case, we're going to use the ratio test. So if an, in this case, first of all, you have to write an. What is the nth term on this? 1/1 over what? N factorial. Pretty nice. I mean, we're saying this is 1, that's 2, that's 3, so it correlates pretty nicely. So what does an plus 1 equal to?
1 over n plus 1 factorial.
N plus 1 factorial. So now you're looking at, you look at again, the limit as n goes to infinity of the absolute value of the two. The limit of the absolute value, so you have the limit as n goes to infinity of the absolute value of 1 over n plus 1 factorial all over the absolute value of 1 over n factorial. Does the absolute value actually do anything in this case? Not really. Could it? It might, because you could have a negative sign in there, but in this case, it's not going to do anything. So what does this simplify to? The limit n, like this, you have n factorial over n plus 1 factorial, which is what cancels there. The n factorial cancels, and you end up with the limit as n goes to infinity of 1 over n plus 1. And what does that go to? 0. So what does that tell us?
Converges.
How did it cancel? I thought there'd be a pause right there. I'll do one intermediary step. You ready? Here's the intermediary step. Ready? What does n factorial mean?
N times n minus 1 all the way.
Yeah, n times n minus 1 times n minus 2 all the way down to 1, right? And then you have n plus 1 times n minus 1 down, right? What cancels? Everything. It all goes away except for that.
So for n plus 1, the factorial kind of implies that.
N plus 1 factorial means n plus 1 times n minus 1 times n minus 2. It just starts higher. So everything cancels, it cascades down, and you're left with 1 over n plus 1. What's the limit as n goes to infinity of 1 over n plus 1? 0. So what does that tell you? Is it 1, 2, or 3? Oh, it's less than 1, so it converges. Nice. Now here's the thing. It'll go positive and negative. It'll go doot, 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 doot. It'll get closer and closer to 0, because what's it going to? It's going to 0. So does this represent all possible alternating series? No, because alternating series, they could converge to something else other than 0. They could spike up, they could get bigger, but in this case, if it's getting skinnier, and it's alternating between signs, what's really nice about this? These series always converge if the individual elements, the sequence, is going to 0, and each successive term is less than the one before it. So you only need two things. If it's alternating sign, and it's getting smaller, and it's going to 0, then it definitely converges. So on this one right here, this is kind of cool. What does this almost look like? Is it the harmonic? No, what would you call this one? What would be a better name for this? This is what's the word up here? The alternating harmonic series. And what does this say? Well, we have to test, first of all, what's the limit as n goes to infinity of this thing? What's the limit of this thing right here? Oops. What is it?
0.
It's 0. The top goes plus 1, minus 1, plus 1, minus 1, but the bottom goes. Okay, so that's the first thing. You have to then say, is each successive term less than the one before it? Yeah, you have 1, 1/2, 1/3, 1/4, but you go, what is it? The first term is going to be positive or negative? Positive, then negative, then positive, then negative. Are they smaller? Or did I get that sign right? What do you think? So on this one right here, first of all, what is the an plus 1 equal to? 1 over 2 times n plus 1 factorial. So you could write it as 1 over 2n plus 2 factorial, correct?
Yep.
So what are you looking at? You're looking at the limit as n goes to infinity of, absolute value of, and I'll drop it because it's going to be positive, it's fine. 2n plus 2 factorial over, I'll keep it in there, over, okay, hold on, Lambino, shh, like this. So what does this become? You get a nice numerator now, right? Limit as n goes to infinity of 2n factorial over 2n plus 2 factorial. You have to be very careful about crossing things out here. Tori and I were just talking about, can you, oh, that's, come back. Can you see things now? Oh, that's really helpful. Okay, hold on a sec, kids. Technical difficulties.